Welcome back to Calculus 1. This is part 2 of our lecture on the limit laws. In part 1, we left off talking about limits with indeterminate forms with an example where we were mentioning an algebraic trick, factoring the function before evaluating the limit. Before we get into the following examples, in this part, we'll start off with a very brief review of factoring methods. All right, now ideally your factoring skills are top-notch. Hopefully you use that a lot in your pre-calc course. Hopefully there wasn't a long gap from when you last had your last course and then used factoring. So if that was the case, here we have some very basic, quick examples on that. This is a great thing to follow with me or your instructor on to review factoring. So our basic goal here is to factor quickly a quadratic polynomial, what in algebra you would have called a trinomial of the form ax squared plus bx plus c, where a, b, and c typically are integers, but generally any real numbers. All right, the simplest case is when the coefficient of x squared, a, equals 1. We now have a very simple way to factor. Let's say for this example, x squared, notice a is 1, plus 2x minus 35, we would try to factor this by finding numbers whose product is c, here negative 35, and whose sum is b, 2. So can you think of two numbers that multiply to negative 35 but add to 2? 7 and negative 5. Multiply them, you'll get negative 35. Add them, you'll get positive 2. And those integers here, in the case when a is 1, go directly into the factorization. This polynomial would factor as x plus 7 times x minus 5 using those integers. All right, now that's very simple. So make sure you're extremely comfortable with that. Your algebra skills are, again, usually what determine your success in Calculus 1 and Calculus 2 for that matter. All right, let's take a look at the case when a is not 1. This is what's generally referred to as the AC method. This is a very quick, simple way to factor quadratic polynomials when a is not 1. You might know it by a different name, but it's probably mathematically equivalent. All right, let's say we're trying to factor this example, 2x squared plus 7x plus 6. We modify the previous method above. We try to find numbers whose product is AC, or a times c, and whose sum is b. Here, a is 2, b is 7, and c is 6. So if we multiply a times c, 2 times 6, we get 12, and b is just 7. So we'd be looking for numbers that multiply to 12, but add to 7. Can you find them? Do they exist? If so, this polynomial will generally factor. Those integers are 3 and 4. 3 and 4 multiply to 12, but add to positive 7. So using the AC method, this polynomial will basically factor. Now the work's a little bit different. Here we're going to rely on factoring by grouping, and we use the integers 3 and 4 to split the middle term, 7x, into 4x plus 3x. That's using those integers, but with x attached. And it wouldn't matter here if you thought of 7x, switching the order of addition, as 3x plus 4x. We just use those integers to split the middle term apart with x attached. All right, so we're going to rewrite that above, splitting 7x into the two parts, 4x plus 3x. And what we do is factor by grouping here. We take a look at the first two terms, factor out a greatest common factor, and do the same thing for the second two factors. All right, and your first two terms looks like you can factor out 2x. In your last two terms, 3x and 6, you can factor out just positive 2. So we factored by grouping, and notice the last kind of expression there. Each term contains x plus 2, so we could factor x plus 2 out. The terms or factors in front of the parentheses, 2x and 3, that will be the other factor, 2x plus 3. So we get our factorization here. With practice, this will go really quick. We're going to use this in some following examples. Make sure you're comfortable with this to make the next few examples go as quick as possible. All right, with that out of the way, let's get to example 1. This was kind of our motivating example in part 1 about limits with indeterminate forms. All right, and well, let's try to see what happens here. So we mentioned something about plugging in earlier. Let's try plugging in. And notice what happens. We get 0 divided by 0, which is an indeterminate form. So directly plugging in or substituting x equals 5 doesn't give us our answer for the limit here. Since 0 over 0, it's not a defined function value. Now what plugging in does tell us, it guides us, whenever we have an indeterminate form, typically 0 over 0, that's going to almost always hint or point towards trying an appropriate algebraic trick, or rewriting your function using some basic algebraic techniques. And if you take a look at that numerator, that looks like something that you would factor. So our first algebraic trick that we're going to introduce is basically factoring. Again, an important skill from your algebra course. All right, so the numerator factors as x minus 2 times x minus 5. And we plug that into the problem, rewriting the function into this equivalent form, x minus 2 times x plus 5 divided by x minus 5. Now you would probably automatically, at that expression, that fraction, cancel out the x minus 5s, but we have to be careful. Can we cancel the x minus 5s out? Now you might have been sloppy before, never mentioned this, but we can only cancel x minus 5 divided by x minus 5 to 1. A factor over itself cancels or simplifies to 1. We can only do that if the value of x that we're using here is not 5. So x minus 5 divided by x minus 5 does equal 1, provided x is not equal to 5. So for all values other than 5 for x, this does cancel out to 1. Now, why are we mentioning that? We just want to have a technically correct foundation in Calculus 1 to build upon. And think back to limits. When evaluating a limit as x approaches 5, we are concerned about reaching the case when x equals 5. So through evaluating the limit here, x never equals 5, which means we can cancel the factor of x minus 5 out. If you cancel that out, you're left with the limit as x approaches 5 of the simplified equivalent function x minus 2. All right, and what we can do now this is a simple polynomial that we can plug in. So we're going to plug in x equals 5 to that. And 5 minus 2, we get our limit value here, which is 3. So what we see here is originally the limit had an indeterminate form, 0 over 0, but the limit does work out to be 3. So in some sense here, we could say, for this example, 0 over 0, the indeterminate form, corresponds with its limit value to 3. All right, so this is a very simple example applying one of our algebraic tricks, factoring. We're going to be taking a look at before example 2, which is a 4-part example, some other typical algebraic tricks. All right, just to review kind of what was going on here, to give a technically correct foundation, be careful. We're not saying x squared minus 7x plus 10 divided by x minus 5. We're not saying that equals x minus 5. What we are saying is if x does not equal 5, then those two expressions are mathematically equivalent. They're equal. So just be careful. When you say things cancel or two things are equal, there might be some conditions for which that's valid. And here, x squared minus 7x plus 10 divided by x minus 5, that equals x minus 2 only if x is not equal to 5. That's ensuring that you can cancel the x minus 5 factors out. If we allowed for x equal 5, we have an indeterminate form again, 0 over 0. All right, this was a very simple example. It's a good one to go through together with you. Before we get to example 2, which I'll give you an attempt at with 4 different parts, A through D, let's kind of go through an overview of the typical algebraic tricks that we'll be applying. All right, that first example, example 1, we saw our algebraic trick was factoring. That was the key to that problem. The inverse of factoring, or opposite, is multiplying out or expanding. So those two techniques go together, factoring or reversing it by expanding. All right, those are going to be typically when we have polynomial expressions, the 2 standard things you can do, factor or expand them. Hopefully you're very quickly able to expand x plus 1 cubed. The results on the screen there. You should be able to do that quickly. Be careful, x plus 1 cubed, we can't cube each part to get x cubed plus 1 cubed. In red there is arguably the biggest mathematical mistake that students make through any mathematics course. A plus b to the nth power is not a to the nth power plus b to the n. So just make sure you are comfortable with that. All right, those are 2 basic algebraic techniques or tricks, factoring or expanding, which we'll apply in the next few examples. We're going to start to see some radicals, typically square roots, pop up. And the trick, usually, when dealing with limits involving square roots within the function, typically we're going to rely upon the conjugate. Now, it's probably been a while. Maybe the last time you talked about a conjugate was in your algebra course when you talked about rationalizing denominators, getting rid of square roots within a denominator. By the way, it's totally fine to have square roots in a denominator. If anyone told you otherwise, they were lying to you. All right? So let's say we have this square root expression, square root of a plus square root of b. We define the conjugate of that, basically changing the sign between those 2 quantities. So if our expression is square root of a plus square root of b, the conjugate of that is square root of a minus square root of b. So we basically just change the sign between. All right, now what's the point of bringing up the conjugate? Well, if we take an expression and multiply by its conjugate, what happens is the radicals all completely cancel. We're basically just going to multiply that out. Notice the first terms, if you FOIL, square root of a times square root of a square root times itself cancels to a. Here, due to the plus and minus signs, you get pretty much the same outer and inner terms, which cancel. But what you're left with now is square root of b times negative square root of b. Now, a square root times itself cancels out. Here, square root of b times square root of b cancels to b, but multiplying the signs, a positive times a negative, gives a negative. So our simplified answer that has no radicals left in it is a minus b. And that's something that always happens when you have an expression and you multiply by its conjugate, there's no more radicals. Notice our answer here, a minus b, has no square roots or radicals in it. All right, that's going to be a third algebraic trick using the conjugate. Typically, like you did in your algebra course, you would multiply and divide by the conjugate. Multiplying and dividing by the same thing is multiplying by 1. Multiplying by 1 doesn't change anything. All right, and then a kind of last topic that we'll be getting to, or trick, is using a common denominator, which typically will be applied when we're adding or subtracting fractions. All right, now you might want to pause to copy these down. These are our 4 standard algebraic tricks: factoring, expanding, using the conjugate, multiplying and dividing by the conjugate, and then using a common denominator. When you're ready, we'll advance to example 2, which is 4 parts. All right, and let's go ahead and get to it. Example 2 is simply evaluate each limit, and we have 4 standard examples that you'll see scattered throughout the homework questions and throughout possible quiz and exam questions. These are pretty standard for what we'll be getting to within the next few lectures. So I'd like you to pause the video, make an attempt at all 4 of these. Each one of these examples applies a different algebraic trick. See if you can think which algebraic trick would apply to each limit here, some of which have indeterminate forms. We'll check in several minutes. All right, welcome back. Hopefully you made an attempt at these. For part A, here plugging in x equals 2, we get 0 over 0. Recall, when you have an indeterminate form, 0 over 0, you should be thinking, I'm going to apply an algebraic trick. And here, the relevant algebraic trick is factoring. So this one's a little trickier using the AC method, but it will factor. And here you can see once you factor it, the x minus 2 factors cancel out, and we're left with 1 divided by 2x minus 1. At that point, you can plug in x equals 2, and you get in your denominator 2 times 2 minus 1, which would be 3. So once you cancel the factor, x minus 2, that cancels or eliminates the indeterminate form from that function or expression. We have an equivalent function or expression, 1 divided by 2x minus 1, which now does not contain an indeterminate form. So we get here, our limit is 1/3. All right, let's move on to going through part B. Here, the variable is a little bit different. H is the variable. Notice there's no x here. The name of the variable doesn't matter. Where we last encountered a limit as h approaches 0 was our introduction to calculus, where we said h was the distance between the 2 points, which when that distance becomes small, the secant line approaches the tangent line. Now, I threw this example in to get you comfortable with problems like this when there's h involved, because very shortly we'll be using limits to give a definition of a derivative, whatever that is. All right, so let's approach the problem. If we plug in here h equals 0, we do get 0 over 0. That will point to us to trying an algebraic trick. And here, the only real relevant trick, take a look at that. You have 3 plus h squared in the numerator. That's tempting you to FOIL or multiply that out or expand. All right, and if we do that, first multiply or expand 3 plus h squared, you'll get 9. The outer and inners combine each to 6h, and then you have plus h squared. Now take it kind of piece by piece. Notice the 9 subtract out in the numerator. You're then left with, in your numerator, 6h plus h squared. We still have an indeterminate form there. Notice if you plug in h equals 0, 6h plus h squared divided by h still becomes the indeterminate form 0 over 0. But what we can do is factor an h out, and then you can see that factor of h that we pulled out in the numerator cancels with the factor of h in the denominator, thus eliminating the indeterminate form. We have an equivalent expression for the limit as h approaches 0, 6 plus h. And at that point, there's no more indeterminate form. We can just plug in h equals 0. So we get 6 here for our limit. All right, let's go through part C. Part C is a little trickier just simply because you probably didn't last use the conjugate by multiplying and dividing by it in your algebra course, which might have been a long time ago. All right, if you plug in x equals 10, you do get 0 over 0, an indeterminate form. Since we have a function involving square roots, our algebraic trick is almost always going to be multiplying and dividing by the conjugate. Recall, you have to multiply and divide by the same quantity in order to be algebraically correct. A quantity divided by itself is 1, and you can always algebraically multiply by 1 without changing a quantity, function, or expression. So we start recognizing we have an indeterminate form with a function with radicals in it. We'll take our function, the square root of x minus 6 minus 2 divided by x minus 10, and we're going to multiply and divide by the conjugate of that numerator, square root of x minus 6, but plus 2. Notice at the end there, we're multiplying and dividing by the same quantity, which we're multiplying by 1, which we can do. All right, now the work kind of going down the screen there through each step, you would multiply out your numerators. That contains an expression times its conjugate. Recall, an expression times its conjugate, the radicals should cancel or eliminate, which you can see you're left with in the numerator x minus 6 minus 4, no more radicals in the numerator. And then we're going to keep our denominators factored when we multiply them. That's a good tip. Only keep part of your expression factored, typically the part that doesn't have the radicals originally. So since originally we had no radicals in the denominator, we might be thinking we want to keep our denominators factored at this step. You'll probably see why in the next one. All right, now our numerator right now is x minus 6 minus 4. Combine those like terms to get x minus 10. And the reason why we wanted to keep our denominator factored here is so we can see that the factor x minus 10 cancels out. And what we have is the equivalent expression or function 1 divided by the square root of x minus 6 plus 2. Now, ignore any temptation to get rid of radicals in the denominator. You would just be going backwards to the function that we started with. We're using the conjugate here for a different reason, to eliminate the indeterminate form. And at this last step there, now we can plug in x equals 10. And if we do, the square root of 10 minus 6, square root of 4 becomes 2. So within our denominator, we get 2 plus 2. Our denominator becomes 4, giving us the limit, the end result or answer of 1 over 4. All right, let's go through the last example, part D. This one doesn't involve indeterminate forms since we have division by 0. But what this does kind of relate to is our earlier limit laws. Now, this is a little bit different, but it's still an algebraic trick, so I wanted to include it within this 4-part example. Using a common denominator is a pretty frequently applied algebraic trick. And what we're going to try to think is the individual parts, 1 over x and 1 divided by x times x plus 1, individually those limits each do not exist. Now what that means is we cannot apply the limit laws by splitting this apart to 2 separate limits, since here each limit does not exist for the pieces. So our alternative to applying the limit laws is to try combining with another algebraic trick and simplifying it. Here we're subtracting fractions. The algebraic trick is using a common denominator. Combine those 2 fractions into a single fraction. So we can just use the LCD as x times x plus 1. The first fraction, 1 over x, we would multiply and divide by the missing factor, x plus 1. And then if you multiply and subtract notice your numerators, you'd have x plus 1 minus 1. That's subtracting your numerators. X plus 1 minus 1 simplifies to x. And then notice within that second to last expression, the factors of x cancel out, leaving you with 1 divided by x plus 1. All right, now that's an equivalent expression to the original one. If we use that below in the limit, we have rewritten in an equivalent form our original function as 1 divided by x plus 1. The indeterminate form was eliminated there, which basically allows us to plug in, substitute now, what x is approaching. We're going to plug in x equals 0. This final expression, 1 over x plus 1, would evaluate to 1, which is our limit here. All right, now all 4 of these examples involve the 4 standard algebraic tricks. There might be other algebraic tricks, but within a Calculus 1 course, that's probably enough to get you through almost everything you'll encounter in homework, quiz, and exam questions. All right, now let's get to kind of the next and last part. The section and lecture on limit laws, there's a final part introducing something called the squeeze theorem. So let's motivate this with an actual specific example. The limit as x approaches 0 of x squared times cosine of 1 over x. Now notice what happens when you plug in x equals 0 to the cosine function, cosine of 1 over x, you get division by 0. Cosine of 1 over x is undefined when x equals 0. So something's going on with this. All right, now what we could do here is try to apply the limit laws, split this up as an individual limit of x squared, and then an individual limit for cosine of 1 over x. Unfortunately, while the limit as x approaches 0 of x squared does exist, it's 0, the limit as x approaches 0 for the function cosine of 1 over x, that limit does not exist. So we can't apply the product rule or product law from the limit laws to this example. One of the factors, those limits, does not exist. Now, why is that? This is a very complicated graph and function. I at least want to give you some basic ideas that you might be comfortable with from your pre-calculus course. Think of the graph of cosine of x. Now, there's kind of the amplitude. The graph stays between 1 and -1. Cosine of x, we would say, has an amplitude of 1. And then inside cosine of x, any additional factors multiplying x affect the period, either inducing or causing a horizontal stretching or compressing. Now, what happens when we replace the inside of cosine with, instead of x, cosine of 1 over x, the period is changing very, very rapidly near 0. Now, graphically, what happens, and this is hard to sketch by hand, but this is a here mathematically generated graph, which is a lot nicer than what I could draw by hand. The graph here of cosine of 1 over x is basically like the graph of cosine of x when you're far away from 0. What happens near 0 is the graph for cosine of 1 over x has a very rapid oscillation. Arguably, you can see here, it's jumping back and forth very quickly between the y values 1 and -1. So it seems as we get closer to 0, the function or output values rapidly bounce back and forth between 1 and -1. That's a very loose and kind of a simplified way to explain why the limit for cosine of 1 over x as x approaches 0 does not exist. All right, now let's go back to the problem. All of our current tools don't seem to work. We can't apply the limit laws. There doesn't appear to be an algebraic trick. Factoring, expanding, using the conjugate, common denominator don't seem to apply here. What do? Well, fortunately, there's something called the squeeze theorem, which this example motivates. So we need an alternate rule or method, which is what the squeeze theorem will do. All right, so let's go ahead and state what the squeeze theorem is. The goal with the squeeze theorem is to evaluate the limit as x approaches a of a function which we usually write arbitrarily, generally as f of x. So our goal is to evaluate right now the limit as x approaches a of some function f of x. All right, now the first part of the statement of the squeeze theorem is it says f of x is between greater than or less than two other functions, g of x and h of x. Now graphically, we have an illustration of what's going on here. So graphically, we would interpret that inequality as f of x is in the middle, h of x is an upper function, g of x is a lower function. And that's going to be valid for kind of at least all values of x in an interval around a being what x is going to be approaching. All right, the second part of the squeeze theorem, this is after the and, we have the limit as x approaches a of both g of x, the lower function, and the limit as x approaches a of h of x, the upper function. Those are equal, and we're saying they equal some limit L. Now graphically, what happens? Why is this called the squeeze theorem? Well, if g and h are your lower and upper functions, if they have the same limit as x approaches a, that's basically squeezing or pinching the graphs of g and h together. Hence the name, the squeeze theorem. Now how we make a conclusion is if if f is squeezed between g and h of x, and the upper and lower functions have the same limit as x approaches a, the function in the middle, f of x, has no choice but to be squeezed and have the same limit as x approaches a. So if those conditions are met, the condition regarding the inequality for f of x, and the second condition with the limits of g and h, the lower and upper functions being equal, we reach the conclusion the function squeezed in the middle, f of x, has the same limit as x approaches a, which notationally, we're writing that limit here, or common limit, as L. All right, this is a standard theorem introduced early on in a Calculus 1 course. Seems really nice. The problem with this is it requires you to have the inequality statement already. F of x, your function of interest, is squeezed between a lower function g of x and an upper function h of x. What this doesn't tell you is how you would construct or find that inequality. Let's get to example 3, where we'll see all that in action. Now, maybe you kind of see how to approach this. So if you'd like, make an attempt at this, but this is probably one of the more challenging examples. Maybe pause the video, give yourself about a minute to attempt it. We'll check in shortly. All right, now our first step here, as we go through this, is in order to apply the squeeze theorem, we have to find that squeezing inequality, our function here, x squared times cosine of 1 over x, has to be squeezed between two functions, g of x and h of x. There's no necessarily straightforward rules and ways to find those. But let's start with some basic inequalities related to our functions here. Now, the one we're going to build and start from is a basic fact from pre-calculus about the graph of sine and cosine. Both of them have an amplitude of 1. Graphically, the graph of sine of x and cosine of x stay between 1 and -1 on the y-axis. Now that's giving us some sort of inequality. But our function involves cosine of 1 over x, not cosine of x. All right, so what we can do is make a replacement, x with 1 over x. That's affecting the inside of the cosine function. Changing something inside affects the period, a horizontal stretching or compressing. It doesn't change the amplitude. So cosine of 1 over x is still between -1 and 1. That looks a little closer to our function. We now have cosine of 1 over x. But notice what we're missing. Our function has a factor of x squared. So what we can do is multiply all three parts of this by x squared. X squared's positive. Multiplying a compound inequality by a positive number wouldn't cause any of your inequality signs to flip. So if we multiply the inequality above by x squared, we get to here. And now the inner part is our function for the limit we're trying to evaluate. We now have x squared times cosine of 1 over x. So this is the first part of applying the squeeze theorem. We now have an appropriate squeezing inequality. All right, what we need to check is that the lower function, negative x squared, and upper function x squared, each have the same limit here as x approaches 0. So if you check, plug in, since both negative x squared and x squared are polynomials, they each have a limit of 0 as x approaches 0. And now we're in business. We have our inequality. Our function is squeezed between two other functions, negative x squared and positive x squared. And the upper and lower functions have the same limit as x approaches 0. By applying the squeeze theorem, we reach the conclusion the function in the middle and its limit has to approach the same thing. So the limit here as x approaches 0 of x squared times cosine of 1 over x equals 0, following from the squeeze theorem. Now, this is one of the harder examples to apply the squeeze theorem with. There are likely some simpler examples in the homework. You would want to check to apply the squeeze theorem that the upper and lower functions have the same limit as x approaches a, whatever that value of a is for the problem. So make sure to check that before applying the squeeze theorem. Check that your upper and lower functions have the same limit.